Hello everyone, this is going to be the solutions for the worksheet of the week 2. So in the first exercise we have that we can evaluate a limit when x goes to infinity, and clearly we have a situation where we have a subtraction of two things that are infinity, so infinity like minus infinity. So this is what we call an indeterminate form. We cannot keep this way, so we need to find a way to remove the subtraction of infinities. I cannot tell whether infinity is going to be bigger, so the subtraction is something that I cannot make. So what's going to happen is that I'm going to multiply by the conjugate doing the difference of the squares, right? So I'm going to leave this one as it is, but then I'm going to multiply by the same thing up and down, but with the opposite sign. So minus here, then this one is going to be with a plus. And so this is x cubed. And so I want this thing not to change. And so essentially I need to multiply by 1. And so if I multiply by the same thing up and down, then this is just like multiplying by 1. But by the effects, remember this is a difference of the squares on the top. So this is going to transform into the limit when x goes to infinity, and the roots are going to cancel. And now I'm going to have x to the 6 plus 5x to the 3 minus x to the 3 squared, which is x to the 6. So this is going to transform into this. And below I'm going to keep what I have. And so at this point, notice that I can cancel out this x to the 6, and I'm just going to keep 5x to the 3, which is good because that's going to allow me to divide up and down 4x to the cube. So now I'm going to have here 5x to the cube, but I'm going to divide by x to the cube there. And so I'm also going to divide by x to the cube inside of this root, which is essentially saying that I'm going to divide by x to the 6. And I'm gonna divide this x to the cube by x to the cube. If you're confused about this step, remember that x to the 3 is square, right, is x to the 6. So if I do root of x to the 3 is square, is just the root of x to the 6. Or in another way of seeing it, x to the 3 is just root of x to the 6. And so I'm just representing x cubed as square root of x to the 6, so I can fold it inside this. Now I can do limit when x goes to infinity, and so because I'm dividing, this becomes a 5. This one in here becomes root of 1 plus 5 over x to the 3, and then this becomes 1. Notice that when x goes to infinity, this term goes to 0, and this becomes limit. Sorry, I'm plugging already. So since I'm plugging the infinity already, and this part is going to 0, this becomes 5, the square root of 1 plus 1, and so this is 5 over 2. That'll be the limit for number 1. Now, number 2, we have a bunch of different limits, and they're going to infinity, minus infinity, and 0. So we can use the information that we have here. So the limit when x goes to infinity of this, notice that is infinity over infinity, but we can just rewrite this as limit when x goes to infinity of 1 over x squared minus x, right? X cubed over x squared is x. This part goes to 0, but this part is going to go to minus infinity. So nothing to do there. By the same reason, if we're going to minus infinity, this part goes to 0, and this part is going to go now to positive infinity. And now if I'm going to 0 by the left side, Notice that I'm taking positive, negative numbers, but that doesn't really matter too much. I can rewrite this expression as notice that the top this is gonna go to 0, so the top is gonna be 1, but the bottom is approaching to 0 by negative numbers. So that means that this is gonna be minus infinity. Okay. Remember that for this type of exercise, you could always do a table to just figure out where things are going, or let me do the table really quick. Although this is not something that you had the opportunity to do on exams, you can definitely do this to understand what's going on. So for example, if I have the function f of x equals 1 minus x cubed divided by x squared. So now you can see here what's going on and how it's going to infinity when x is approaching to 0, regardless if it's the left or the right. Wait a minute, this is x squared, this is actually going to infinity. And I just realized of that mistake because I was checking with the graph. But let's actually figure that out with a table, so you can see how the table is supposed to function. So we can give it a table here, and we gotta make sure that we put here f of x. We define f of x first, so now we're gonna make sure to put f of x 1, so it matches this x1 here, and now it's gonna use this function. So now let's use a value that is close to 0. Let's do 0.1. Notice that that's 0.99. But we need to use negative, so this one, minus 0.1, minus 0.01, minus 0.001. And so, well, this is too large, this one. I already become super large when I'm just 3 decimal points away from 0. And so you can see that this is becoming a larger and larger number, and it's positive. So this tells me that when I'm approaching to 0 in x, this is approaching infinity in y. Okay, and the way that I look at this here with this function, oops. Let me put this here. The way that I look at this is, notice, if I'm going to 0, the top is going to 1, because this is going to 1. The bottom is going to 0, right? But you got to remember that 1 over something that is close to 0 becomes a very large number. So this is what is going to change the quantity. So this is what it makes that the quantity becomes larger and larger. One of the things that we care is what is the end sign. And so that's going to tell me, is it infinity or minus infinity? And here is infinity because the top is 1 and the bottom is still a positive number that is changing. If this were going to be x instead, then you'll see that it will be going to minus infinity because the number will start becoming negative, negative, negative. Will start growing in a negative direction. Okay. All right. So let's move on from this exercise. Now, exercise 3 says, sketch the graph of a function with the following properties. We want that the limit when x goes to 2 is 2. The limit when x goes to infinity, limit when x goes to infinity is 2. So 2 is here. And when x goes to infinity, is getting to here. Is closing this line. We want that when it's minus infinity is 0, so 0 is the asymptote. It says that when we approaching 1, then it's infinity by the left. So here 1, and so is infinity by the left. So we have an asymptote here. We have an asymptote here. We have an asymptote here. And so for now, let me just say, well, if this is coming from minus infinity, has an asymptote is here, so it's like this. It's probably doing something like this. And then it never touches 1 because it has an asymptote in there. Also, 1 by the right is minus infinity, so it's doing this. And it gets to have an asymptote here at 2. So we have something like this. This has a removable discontinuity at 3. So let's say 3 is here. And so what that's going to mean is that there's a hole in here. But there's assistance of the limit. So there's a hole in there. So removable discontinuity, this is true, this is true, this is true, this is true. So pretty much this will be a graph that will work out with those conditions. Sorry for not having a very pretty graph. This is kind of hard to draw here with this pencil. Now, limit when x goes to infinity of e to the minus x cosine of x. So this limit is going to go to 0. And the reason why you know this is because, well, first than anything, e to the minus x go to 0. When x goes to infinity, e to the minus x goes to 0. Okay, limit when x goes to infinity of 1 over e to the x, which is the same that e to the minus x, is that. Now, we can use the squeeze theorem to argue about this particular limit, because there are two ways that you can really talk about this. And it's first, well, the cosine is between minus 1 and 1, right? So now, if we multiply by e to the minus x, then e to the minus x minus e to the minus x, cosine of x, e to the minus x, is between these two. And because we have this, then we know that this, when the limit goes to infinity, minus e to the minus x is equals to the limit when x goes to infinity of e to the minus x. They're both going to 0. So that implies, by the squeeze theorem, that the limit when x goes to infinity of e to the minus x cosine of x is 0. Okay? This uses a lot the information that the cosine of x is between minus 1 and 1. This is one of the key things that you're using in there. Another thing that you might think is, well, cosine is going to be bounded. It's not going to be bigger than 1. And e to the x goes to infinity. So you might argue in that direction, but this is the easiest direction to argue about this limit. Now, exercise 5. We have f of x equals 2 over x minus log of x. Find each of the following limits. So limit when x goes to infinity. So when x goes to infinity, this goes to 0, this goes to 0. So this is 0 minus 0. So it's 0, so this is fine. So now we care about, let's say, 1 and 0. So let's go with 0 first. When 0, this is going to infinity over, and log when it's going to 0 is going to minus infinity. So this part is going to 0. So this term, 1 over log of x, goes to 0. But this term goes to infinity, and it's because it's 0 is positive, so it's taking numbers that are close to 0, small numbers close to 0, but positive. So this limit goes to infinity. Now, limit when x goes to 1. The log of 1 is 0, so this clearly is going to go to infinity. And this is going to go to 2. So on both cases, for the positive and the negative, this is going to go to 2, and then minus, and 2, minus, and then we care about where this is going. And so the thing is, when we're taking 1 by the left, we're approaching with small negative numbers. So let's actually use the graph over here. Let me change this to log of x. So I'm approaching 1. So I'm using these values, and you can see here that this is a very small value. So they're large numbers. They start increasing to large numbers, but to very small numbers, to very close to 0. Okay, so when approaching 1, we're approaching 0, and this is being negative. So notice that when we're approaching by the left side, this is a negative number that is approaching 0. So this being negative number, this means that 1 over log of x goes to minus infinity. Okay, you can see if you instead take this 1 over log of x, you'll see that this every time is taking numbers that are larger and larger but negative. So this means it goes to minus infinity, and so minus with the minus that is in front is going to end up being a plus. I'm kind of writing this, but at the end of the day, this is just infinity. Infinity plus something is just infinity. Now, if I take in numbers by the right side, I'm taking numbers that are bigger than 1. So for example, 1.1, 1.01, and 1.0001. So as you can see, larger and larger number, but positive. So what that means is that this is going to be infinity positive. With this minus is minus infinity, and 2 minus infinity, that's still minus infinity. So that too is not going to account for anything. Now, number 6, we have to draw pictures explaining the expression this. You got to remember that what this is the limit when h goes to 0 of f of x plus h minus f of x over x plus h minus x. And what is this? Well, this is the slope of the secant line between 2 points, but you're making the distance between those two really small. So what's happening is that you have a function, and then you have x here, and then you have x plus h here, and then you take in this slope of this secant line, right? This is the slope of the secant line, and so when you make h goes to 0, then you're getting closer and closer to x. So when you're getting closer and closer to x, when h goes to 0, what happens is that x plus h is so close to x that there's no difference. And so the secant line becomes a tangent line. Okay? And this is what explains this expression here. And of course, the slope of the tangent line ends up becoming the derivative. Now, here says find an equation to the tangent line to the graph 2x plus 1 at x equals 4. When calculating the derivative, use the definition. So we pretty much need to use this definition. So the way that we're going to do it is we're going to calculate what f of x plus h is, which will be the composition of this. But instead of where x is, I'm going to plug x plus h. And this is what happens. Oh, but we don't really need a specific x because we want to calculate to x equals 4. So we can use it with 4 here. So instead of using 4x plus h, I'm going to use 4 plus h. And so 4 plus h will be 2 times 4 plus h plus 1. That I can actually find out what that is. This is 8 plus 1, 9. So this is 9 plus 2h. So this is what f of 4 plus h becomes. Now remember what is also f of 4. F of 4 is plug 4 here. 2 times 4 is 8 plus 1 is 9. So this is the square root of 9. This is 3. And so if I'm going to make the derivative, I want to find out f prime of 4 really. That's what they're asking here. This is the limit when h goes to 0 of f of 4 plus h minus f of 4 over h. It turns out this is limit when h goes to 0 of 9 plus 2h minus 3 over h. Do you know this type of limit? Because you've seen it before. We need to use conjugate to be able to make it so it's not 0 over 0. And so we want to get rid of the root. And so we multiply up and down by 9 plus 2h plus 3. So we can make the difference of the squares. Now at this point, then that transforms the limit in 9 plus 2h minus 9 over h square root of 9 plus 2h plus 3. So the 9 gets cancelled with the 9. And on the next step, I'm going to be able to cancel out the h. And so the problem of having a 0 on the denominator is going to disappear. So I can eliminate this. I have limit when h goes to 0 of 2 over 9 plus 2h plus 3. And if I plug 0 here, then notice that this becomes 2 over square root of 9 plus 3. So this is 2 over 6, which is 1 over 3. And that's it. That will be the derivative for the function at this point. Now let's transition to question 8. It says, sketch the graph of a function that has the following properties. F prime is equals to on the interval 1 to infinity. F of x is continuous but not differentiable at x equals 1. F has a removable discontinuity at x equals 0. And f of x has a jump discontinuity at x equals 1. And the limit when x goes to minus infinity is 0. So a bunch of different things. So I can start with the asymptote being 0. Also says f has a jump discontinuity at x equals minus 1. So that means that at minus 1 there's a change between the values and there's a jump. Let me make a jump like this. Like this is a jump discontinuity. At 0 we have a removable discontinuity. So this means that there is a hole in here, but the function continues. And then because of the asymptote I can do this. So the asymptotes account for that. Jump to discontinuity minus 1, we got it. Removal discontinuity as x equals 0, we got it because the limit exists, but there's nothing in the definition of the function. It says f is continuous but not differentiable at x equals 1. So if that happens, that means that we have a peak. So because we have continuity but not differentiability. So that means that we have this situation. We have a peak here at x equals 1. That makes it continuous. Yeah, the limit when you're approaching is the same as the definition of the function, but a peak is a point where the function is not differentiable because the lateral limits of the derivative are going to give me different values. And also says f prime of x equals f prime of x is equals to on the interval 1 to infinity. So this is talking about the slope of the tangent line. So actually this is gonna change completely my behavior because this is telling me, hey, there is a slope and the slope is always 2. So if the slope is always 2, it means that that there is a line in the way that this behaves. So and it has a slope of 2. So I gotta have something that go faster. So something like this. In this way, f prime. Remember, f prime of x equals m equals 2. This means 2 is the slope of the line, of the tangent line. But if the slope is always the same, it's because the function is a line. So it's always 2x plus something. Okay, there's the peaking here. The peaking here, I still have the peak, and so it's continuous but not differentiable, and it means that after that it has to be a line. So it's always the same derivative. Okay, so this will be the type of graph that you will encounter in this. Now in exercise 9 we have some more graphics. It says below the graph is the graph of a function f of x, and here we gotta choose what could represent the derivative. Notice that this is a line, so this has a constant derivative. This has a slope, and that derivative is going to be that slope. So that means that for the derivative before 0 is going to be constant. So this could be the case, this could be the case, this could be the case, all of this could be the case. This is fine. Now, why this from 2 to infinity, or to 2 to 5 at least, this is a constant function, so the derivative from 2 onwards should be 0. So this means that this can be, but all these others can't be. So this cannot be, this cannot be, this cannot be, because the derivative of this piece, which is constant, should be 0. So it can be either this or this. Now the function is kind of smooth, but there's a discontinuity here. So because there is a discontinuity, it means that the derivative does not exist. And so if the derivative does not exist, it's because the lateral limits of the derivatives, they're different. And so it cannot be this one, because this means that the derivative here will have the limit will exist in here. So this will mean that somehow I could have something coming from here. So it gotta be this function here. This is the only one that is going to account for being the derivative of all this. Also notice that the tangent line of this is negative, is going in this direction, the tangent line, and that kind of makes sense with this. It kind of also makes sense with this, but you're gonna also see that the slope should be negative, and the slope of this is negative, while the slope of this one is positive. Even if so, the function, sorry, the derivative is positive, even if this is decreasing. So this will be the solution to exercise 9. Now for exercise 10, we use a squeeze theorem, and this is going to be similar to one that we did before. The whole thing starts from the fact that sine of 1 over x is between -1 and 1. And so because of that, then I can bound it by -1 over x squared. Then I can multiply all that. And because I can find the limit when x goes to 0 more easily for this ones, thanks to this limit, when x goes to 0, this part goes to infinity, and e to the minus infinity is going to be 0. So all this is 0. And so this means that this goes to 0, and this goes to 0. And so that implies, by the squeeze theorem, that the limit when x goes to 0 of this is 0. Notice that the key thing is that we cannot compute the limit directly. and we're using a sign, so that's what it tells me that I could use the squeeze theorem. So remember, at some point or somewhere you should put squeeze theorem. Now here we have the intermediate value theorem. We want to show that the equation x squared equals 1/2 have a solution on the intervals 0 to 1. So the best way to do that is create a function. We can create a function f of x equals x squared minus 1/2, and then we're going to find out a 0 for this function. And so first we can plug at 0. So f of 0 is minus 1/2, and f of 1 is just 1 minus 1/2 is positive 1/2. So because this function is continuous, so f is continuous, and f of 0 is negative, but f of 1 is positive, there should exist a number c, that is in the interval 0, 1, so that c squared minus 1/2 is 0. And this is by the intermediate value theorem. We have one value that is negative, one value that is positive, so at some point it gotta cross 0. That's the logic. If the function is continuous, if it doesn't break, and I have one value that is negative, one value that is positive, that it means that at some point it crosses 0. And that's what we find out here. That for a certain c, then it's going to be a solution, and we're going to have a 0 of this function. And if we have a 0 of this function, then that solves c squared equals 1/2. Which, by the way, is obviously going to be the number c equals 1 over square root of 2, which is what I get when I do square root of this. And it's the positive because we are in the 0, 1 interval. Now, last but not least, we have the exercise for continuity. We have the function f of x equals x squared minus 1 and log of x, and they are split by the number 1. So when it's x less than 1, we have x squared minus 1, and we have log of x when x bigger than 1. So clearly both of these functions are continuous. The problem is 1. The joining point is where we have the issue, right? So this is something that is likely going to look like this. In 1, we have log after 1. Log in 1 is 0, so it's like this. It doesn't include 1, so it needs to be a hole in here. And then for less than 1 is x squared minus 1. So x squared minus 1 starts here at 1, and then it opens up like this. Okay. My drawing skills with tables. God damn it. Okay. So instead, let me use Desmos so you can understand what the hell is that I'm trying to do. So I'm gonna do f of x equals log of x, and I'm gonna put x bigger than 1, and I'm gonna put now g of x and of course put x lesser equals than 1. So now you see it there. This is what is supposed to be, wait, x squared minus 1? Oh yeah, it's x squared minus 1, not 1 minus x squared. So I had this all wrong. So this is a function, and so you see that it's joining here. It looks like it's going to be continuous. Okay? It looks like it's going to be continuous because the joining is nice. Now let's prove that that is true. So this is I was doing 1 minus x squared instead of x squared minus 1. So this is all wrong. But you know, graphic design is my passion, right? So it gotta be something like this. Anyway, so to prove that this is continuous, I want to prove that the limit when x goes to 1 of f of x is equals to f of 1. And so first, where is f of 1? Well, f of 1 is defining here. F of 1 is 0 because it's 1 squared minus 1 equals 0. And now the limits by the right side of f of x is the limit when x goes to 1 of log of x, and that's 0. And the limit by the left of f of x is x squared minus 1, which is also 0. And so in this scenario, we have that both lateral limits coincide, and so this happens. And so this means that the definition of continuity holds. And also the function is going to be continuous everywhere because all these functions are continuous in every single point. The only point that it was troublesome here, it was the joining point. But turns out that the joining point was also complete. And so this is going to be a function that is continuous. Now, when they ask me if the function is differentiable at x equals 1, it's a different question. And there are multiple ways of approaching this. One of the ways would be by analyzing what the derivative is. And so this is something that you can do once that you have the definitions of derivatives. This is 2x for x less than 1. And 1 over x for x bigger than 1. As you can see, when we're approaching 1, this function is going to be approaching 2, and this function is going to be approaching 1. So actually, we're not going to have, we're likely not going to have differentiability at x equals 1. Okay. You can look this, of course, by the definition, doing lateral limits. You do lateral limits by this side and by this side, and you see that the limits that you're going to obtain are different. So, of course, we do not have differentiability in there. Okay, and so this is the end of the worksheet solutions for week 2.